Okay, calculus students, here we go with section 5 of chapter 2, and we're looking at implicit differentiation. So let's rock and roll. We've got a couple days on this. One maybe is just to even talk about the words explicit versus implicit. If you look at a definition for explicit, it refers to things that are fully or clearly expressed or demonstrated. It leaves nothing to be implied. So it's kind of just, very, very clear and in your face. Much like if I write the equation y equals 3x squared. That would be an explicit equation. It defines what y is. Y is equal to 3x squared. Implicit, on the other hand, has the definition. We're going to look at definition for number 4 here. In the case of mathematics, an implicit means having the dependent variable not explicitly expressed in terms of the independent variable, like we were talking about here. Y is our dependent variable and x is our independent variable, right? So the dependent variable is defined in terms of the independent variable. Well, we can get equations that, I've just got a bunch of different equations here, but which ones of these are implicit? Well, they're the ones that aren't explicitly defined. So this one here, definitely implicit. And it would be rather tough to this should say y here. It would be really tough to just solve for y on that. And so that would be an implicit equation. Here's another example, a great example of an implicit equation. This one, explicit, y is defined in terms of x. Another explicit, y defined in terms of x. Easy, y is equal to x to the 1/2 power. This one would be easy to switch. So while it looks implicit here, I could very quickly convert that into an explicit equation. So we are going to be working with those equations that are implicit, meaning we cannot separate the x and the y very easily. There are some steps that go with this idea of implicit differentiation. And one of them is we'll just differentiate both sides of the equation with respect to x. Well, what does that mean? Well, it means what I'm going to be doing, like if I have a dependent variable y, then I'll end up with this notation dy dx, where the dx shows I'm with respect to x. All right, so we will differentiate both sides of the equation with respect to x, and I may end up with some dy dx's on each side. What I'll next want to do is collect all the terms with dy dx on one side of the equal sign, and the other terms, put them over to the opposite side of the equal sign. Once I have my dy's dx's sorted out, I'll factor out the dy dx. And if I have it on the left side, then I'm going to factor it on the left side. So it will be much akin to doing a GCF, where we'll look for that dy dx in common to all the terms and factor it out. And finally, our last thing, we will end up solving for dy dx. These steps will be a little clearer as we go through it, so hang on. First equation, x squared plus y squared equals 25, and it says find the slope of the tangent line at the point 4, 3. Well, that's going to come second after we get done taking the derivative. If you notice, this is the equation of a circle, isn't it? And I could handle this either in an explicit manner or an implicit manner, because I could solve this for y squared, couldn't I? I could say y is equal to plus or minus the square root of 25 minus x squared. But what I've just kind of created is really two equations out of this circle equation. And I really would have to pay mind to each of them and take their derivatives. That sounds like a little bit of work. I wonder if implicit method might be a better way to go. So with the implicit method, I don't need to sort out my x and y's. I'm just going to take the derivative of each side. And like we've been doing in the past, the derivative of x squared is 2x. Now I'm doing it with respect to x, so it'll be just 2x. However, when I encounter a y variable, this now will look a little different. I'm still going to use my power rule. It's going to be 2y, but now that took care of the power of 2. Now I need to take the derivative of y. And the derivative of y, since it's the dependent variable, is going to look like dy dx. This is multiplication going on here, so I could put parentheses if I wanted to, or I can just leave them sit side by side and have the implied multiplication. The derivative of 25 is 0. So that was kind of step 1, take the derivative of every term. Step 2, I talked about isolating dy dx. So let's isolate dy dx. Isolate terms with dy dx. How do I do that? Well, I use algebra. I'm going to keep the 2y dy dx on my left side, and that means then I'm going to subtract 2x and bring it over to the other side. So this will look like minus 2x there. So I get this so far. That's like a step 2, isolating the dy dx. Since there's only one term, I can skip really level 3, step 3 that we were talking about, but we can go straight to 4. Let's solve for dy dx. And to do that, we're simply going to divide both sides by 2y. So I get dy dx is equal to negative 2x over 2y, which would simplify into negative x over y. And we're done. We were able to take the derivative and come up with an answer. Now what you're going to notice is our answer, I'm going to take off this extra one, is in terms of x and y. If I wanted to find the slope of the tangent line, the slope of the tangent line at a point, because we need a location where this is being questioned, at 4, 3. I get dy dx. If I draw this straight line and I can put this ordered pair down here, it means I'm taking the derivative and evaluating, is what the straight line stands for. I'm evaluating at 4, 3. So I put in my 4 for x and I put in the 3 for y, and there is the slope of the tangent line evaluated at 4/3, or 4, 3, the ordered pair. Try another one. Not much more difficult as far as an equation goes. So let's take the derivative of this first item. It is the dependent variable. This is going to look like 2y times dy dx plus the derivative of 3x we know to be just 3, and then that's going to equal 2x. And you might be like, well, why don't I have to do any dy dx on these? Well, it's because x is our dependent variable. We are taking the derivative with respect to x. If you wanted to, you could say that you have the derivative of x with respect to x, but that's going to look like a dx over dx, which essentially cancels and makes 1, reduces down to 1. So for most of the time, I just wouldn't write it. It's not necessary. Now, we have done our derivative step. Let's isolate the terms with dy dx in them. And from what I can see, I need to keep this term over here, and I'm going to get rid of the 3 by subtraction. So I'll get 2y dy dx is equal to 2x minus 3. Now let's solve for dy dx. And that's going to give us dy dx is equal to 2x minus 3 divided by 2y. Can I cancel the 2's? Heck no, not with subtraction sitting up on that top. Okay, so there's our answer. We are done. 4 little steps. Take the derivative with respect to x, and it says the key to doing implicit differentiation is to use your derivative rules on every term, remembering to use the chain rule when necessary. Also product rule, quotient rule, all of those. that we've studied. So we're just going to take this, term by term. The derivative of x squared would be 2x. And then I encounter a little bit of a bump in the road. I notice this next term has x times y. This is going to require the product rule because I have two things multiplied, and the only way to take the derivative of two things multiplied is to use your product rule. So you know what I'm going to do? I'm going to put that negative sign down, and then now I'm going to focus on my product rule here. The product rule, derivative of the first would give me a 1 because the derivative of x is 1 multiplied by the second term, which is y, added with derivative of the second term, which is derivative of y, would be a dy dx multiplied by the first term, which is x. Add with that the derivative of, I'm switching now, derivative of y squared. This is a dependent variable. It's going to be a 2y. Power comes down, reduces by 1. But since it's a dependent variable, it's going to be a dy dx as well. Kind of a chain rule idea there. And the derivative of 3 is 0. Anytime I'm encountering y and I'm taking the derivative, I am going to have a dy dx. All right, cleanup round. Let's just distribute our negative. So I get negative y minus x dy dx. Organize that so it looks nice. Plus 2y dy dx equals 0. Okay, let's keep the terms with dy dx on one side and move the other terms. So we're going to slide over the 2x, subtract it to the other side, and I'm going to add the y and move it to the other side. Nice simple algebra. Yet that will zero out 2 minus 2x, negative y plus a y would be 0. So this is going to come down. I'm going to get negative x dy dx plus 2y dy dx is equal to negative 2x plus y. Followed up by GCFing. Let's GCF out the dy dx, right? It's in common to two terms, here and here. So let's GCF dy dx. That'll leave me a negative x plus 2y. And the same on the right, it does not change. Solve for dy dx. And I will have dy dx is equal to, I'm going to rearrange this and just call this y minus 2x. And I'm going to divide by this other, which I could rearrange it to and have my positive first and my negative second. Right? It looks the same. And there's our answer. Dy dx. The derivative is y minus 2x divided by 2y minus x, the quantity of that. All right, take the derivative with respect to x. I see quotient rule. Do you? I definitely see quotient rule. So I could do quotient rule, and sometimes I tend to avoid quotient rule. So actually, what I'm going to do, I'm going to take and multiply by a 2 plus y on each side. And then I can change this up into a product rule, which I kind of have a preference for over quotient rule. Is that legal to do? Sure it is. I cleared my denominator by multiplying by the full denominator, brought it up to the other side. Now I can go into product rule, can't I? Product rule here on the left. So product rule, derivative of this first thing. Well, the derivative of 2 is 0 and the derivative of y is dy dx. Multiplied by the second. Addition in between our product rule. Now derivative of the second thing would be 6x multiplied by the first. Got through that, and then now we're on the right side of the equation. Derivative of 2 is 0. Derivative of negative y will be negative dy dx. What do I need to do next? I think I'm going to just write this a little bit cleaner. I'm going to bring my 3x squared dy dx to the front there. I'm going to distribute and get plus 12x plus 6xy equals my negative dy dx. Not completely essential in doing, but I like it because it's just kind of cleaned up the work for me. All right, let's isolate. Look at it, LAT, isolate dy dx. So I want dy dx on one side and everything else over. So we're going to add this dy dx over. So I have 3x squared dy dx plus dy dx. And that was through bringing that to this side. Now I'm going to send these guys over to the other side through subtraction. So I'll have a negative 12x minus 6xy. Check out the algebra on that. Make sure you understand it. We have the dy dx terms on the left, and now it's a GCF step. Let's pull the dy dx, and that's going to leave us a 3x squared plus 1. Right? When I pull this forward, GCFing, I have to have something to hold its spot. That requires the 1 there. Negative 12x minus 6xy. Solve for dy dx. So dy dx is equal to negative 12x minus 6xy divided by the group from the left side, 3x squared plus 1. And there's our answer. I'm kind of doing, you can't see it because well, you only get my voice, right? But in my brain, I'm kind of thinking I have some GCFs going on here. I could pull a 6x from that. And if I pulled that 6x, would it be an advantage? And I'm basically thinking, no, not really. Right? There's the GCF of it. And when I look at the bottom, will 6x go into these terms? No. So there's really no simplifying that can happen. This wouldn't be entirely necessary then. But I did have that thought go through my brain and double check to make sure I can't simplify. All right, that brings us to day 1 homework, and it is from page 146, and those are the numbers that I'd like you to practice with. Okay.